In this video, we're going to talk about carbocations. What's a carbocation? A carbocation is simply a carbon compound which is a positive charge and 6 electrons. It's a very reactive species, as you can imagine, since it doesn't obey the octet rule. How do you form carbocations? Well, there are a number of ways to do it, but in this video I want to look at the simplest way, which is simply taking a double bond and adding a proton. So we need a proton, and this proton has to come from a really strong acid like HCl, HBr, or sulfuric acid. We'll talk about the effect of the anion in a little while, but let's just now say that this proton comes from a really strong acid. So what's going to happen? Well, the double bond in the alkene can act as a base, and you can simply add it to the proton. The proton will form a new bond to one of the carbons, and of course the whole thing is which carbon. Now in this case we have ethylene, both carbons are the same, so when we do the reaction it doesn't matter which carbon gets the hydrogen. I'll just arbitrarily say the one on the left over here gets the hydrogen. So here's the new hydrogen. Of course there are two original hydrogens here. This carbon over here would have two hydrogens and a positive charge. So this is our first carbocation. We would call this a primary carbocation because the positive charge is on a N carbon, what we call the primary carbon. Now let's do the same reaction down here with propene, where we also just simply add a proton, but this time we have to make a choice. Is that we have two possible protons that we can form. When the double bond attacks, okay, we get two possible compounds. We can come over here and add the proton to the primary carbon, which gives us a positive charge here, okay, and of course don't forget the other hydrogens. There are a total of 3 hydrogens now on this carbon. There's actually 3 hydrogens on this carbon over here as well, but that's one way of adding it. But we could have added the hydrogen to the middle carbon. So let me just center this a little bit. So we could have gotten another product, which let me just duplicate. I'll come here and start duplicating this one, and we could have instead of adding the positive charge to the N carbon, we could have added it, we could have added it to the middle carbon. So my product could have been, get rid of the charge there, move the positive charge to the end, and of course we have 2 hydrogens on this carbon here. So I have the choice of these 2 carbocations. This one is the primary one. It looks like the one we got from ethylene. This one down here is called the secondary. Now, which one is more stable? Well, it turns out the secondary is much more stable by a long shot. Why? Well, both of these carbons, all 3 of these carbons, have 6 electrons. They have an empty p orbital. They're trigonal planar atom, just shown best up here. There's a p orbital vertically here. Now, what does that p orbital do? Well, it wants electrons, and it wants electrons from neighboring atoms. And indeed, since it's a p orbital, it needs electrons from the neighboring p orbital. But the neighboring p orbital, like over here, is being used to bond the CH bonds. Well, that's okay in a way because you can steal some of these electrons. There's a p orbital here bound for that hydrogen, but that p orbital also overlaps with the empty p orbital here, so we can steal some of those electrons. Each of those methyl groups can donate some small amount of electrons into that carbon. The worst carbocation that you could have at all would be the one just from a methyl group. If you just had this poor little carbocation, it would simply be a trigonal planar methyl with a positive charge. This one can get no possible electrons from its neighbors because hydrogens don't have p orbitals, so there's no way it can donate electrons. This one, this CH bond is lined up so it can shove a little bit of electrons in. But down here, when we have a secondary carbocation, we can steal electrons from both methyl groups. So this one, it turns out, is significantly more stable. Now, these carbocations are very acidic. they have pKa's well into the negative area. The pKa of this protonated ethylene is considered very, very acidic. It's considered to be like minus 24 pKa. Sulfuric acid itself is minus 10. So this is 10 to the 14th times more acidic than sulfuric acid, which says even if you're using a very strong acid here, only a very small amount of that is going to be protonated. Now, when you get down here to the secondary one, it's not as acidic as minus 24. It's the number they quote is minus 18th, but still enormously acidic. What could be more stable than a secondary carbocation? Well, a tertiary one. So what would a tertiary carbocation look like? Well, it'd simply be, you'd start off with 3 substituents to your cation. Now, this one is starting to get a little bit more stable. pKa here is considered about minus 12, which means it's only 100 times more acidic than sulfuric acid itself. So sulfuric acid would form one of these much more easily. This is the whole idea behind the general rule, is that the more methyl groups or more any kind of alkyl groups you got on that positive charge, the more stable it is. So tertiary carbocations are much more stable than secondary. Secondary are much more stable than primary. That's the general rule. Now, what we'll talk about later is what happens with these carbocations when you, and of course what is going to happen is that they're going to look for another source of electrons. What's that obvious source of electrons? The counter anion of that proton. We'll do that in another video.